Maybe let's start.
So then our next talk will be by Shayan on improved trickle-down theorem for arcane complexes and solutions.
Okay, hello. So this is a joint work with my amazing student, Dorna Abdolazimi. She was supposed to come, but she couldn't because of visa issues. So, okay, I'm filling in. So let me quickly remind you about expander graph. Let's say you have a graph, you have a random walker, where maybe at every vertex it jumps to a uniformly random neighbor. So you can look at the transition probability matrix of this graph and its eigenvalues. We know the maximum is 1, the minimum is at least -1. So we say the graph is a gamma expander if the second eigenvalue of the random walk matrix is at most gamma. Now, this talk is about high dimensional generalization of expander graphs to hypergraphs or simplicial complexes. And if this is new to you, this is a theme. This has found a lot of applications over the last decade in construction of locally testable codes, analysis of Markov chains, property testing, condensers, etc. So I want to tell you basically a new method to bound eigenvalues of these high-dimensional simplicial complexes. So first, let me define a few things. So what is a simplicial complex? You can think about it like a d-dimensional simplicial complex is like a hypergraph where maximal hyperedges have d+1 elements of size d+1, and the hyperedges are sort of downward closed. So basically, you can think about vertices as like hyperedges of size 1. We call these hyperedges like faces, and maximal hyperedges, we call them facets. The dimension of a face is the number of its elements minus a 1. So vertices will be faces of dimension 0, edges would be faces of dimension 1, triangles will be faces of dimension 2, and so on. I'm going to use x to denote the set of faces and xi to denote faces of dimension I. So let me give you an example to make sure we're all on the same page. So this is a simplicial complex of a icosahedron. Here we have faces of dimension 0, 1, and 2. 0 are vertices, 1 are edges, 2 are triangles. In the middle, I'm showing to you so-called the Van skeleton of this complex. What is a Van skeleton? It's a graph. Its vertices are faces of dimension 0 or x0. Its edges are faces of dimension 1. Now, a Van skeleton in general is a weighted graph. The weight of every edge is the number of facets that contain that edge. So in this example, the weight of every edge will be 2 because every edge is in 2 triangles. So I haven't written the weights, but yeah, they're all 2. So that's a simplicial complex. We also need the,
Can you remind us what downward closed means?
Oh, if you have a set, you also have its subsets. So good. So we also need the notion of a link. So the link of a face tau is the set of all subsets, say sigma, you can add to tau such that you get a face of the complex, and sigma is disjoint from tau. Another way to think about it is you look at all faces of your complex, you delete tau from them, and then that gives you a new complex, which is called the link of tau. So let's do an example. Let's look at our complex again. Let's look at a vertex. I want to look at the link of this vertex. I want to look at every triangle that has a V and then delete V from it. And then that would give me an edge of a link. And then I will look at every edge that has V. I'll delete V from it. That will give me a vertex of the link. So you actually get this blue cycle. So the link of this vertex is this graph. In general, it would be a complex itself. But now, because I have a 2-dimensional complex, it will be a graph. You can look at the link of maybe one other vertex. This one, it's again a cycle. So in fact, if you look at this nice complex, the link of every vertex is a C5, is a cycle of length 5. Now I can tell you about high-dimensional expansion and eigenvalues. So let's say you have a 2-dimensional simplicial complex. We say it's a gamma 1, gamma 2 local expander. If the link of every vertex is a gamma 1 expander. So the link of every vertex itself is a graph, right? So that graph is a gamma 1 expander. The one skeleton of the whole complex itself is a gamma 2 expander. So again, in our graph, the link of every vertex is C5. C5 is a 0.309 expander. This graph I'm showing here is 0.447. So this complex is a 0.309, 0.407 two-dimensional local expander. Okay? Now you can generalize this to d dimensions, and we say a d-dimensional complex, the gamma 1, gamma 2 up to gamma d, local expander. So you start with faces of codimension 2 or dimension d minus 2. Those ones you want that the link, or one skeleton of the link to be gamma 1 expander. Then you look at faces of dimension d minus 3 or codimension 2. You want their one skeleton to be gamma 2 expander. You go all the way down to faces to the one skeleton of the whole complex. You want that to be gamma d expander. Yeah. The link is not a graph, but the link is graph only for d minus 2. The rest of them actually will be dimension 3, 4, 5, and so on. But I always look at the one skeleton of the link. So
just like the first two levels.
Yeah, the first two levels of the link, yeah. So there are a special family of links here, the links of faces of codimension 2. I call these base case graphs. So these are these are like faces that the link itself is a graph, like the example of the vertex I was saying in the previous slide. And they will be crucial in the rest of the talk, okay? Good. Any other question? Okay, so here is the outline of the rest of the talk. First, I'll tell you a theorem called trickle-down theorem by Oppenheim, which gives you a methodology to use eigenvalues of the base case graphs to bound eigenvalues of the complex. And then I'll tell you our new results and some applications. So what is this trickle-down theorem? It says that if all base case graphs in your complex are, let's say you have a two-dimensional complex, and all base case graphs are gamma 1 expander, and gamma 1 is less than 0.5, then X is a gamma 1, gamma 2 local expander, where gamma 2 is gamma 1 over 1 minus gamma 2, okay? So gamma 1 over 1 minus gamma 1. There is one extra condition that you need the complex to be connected, but okay, I'm not going to get into that for the sake of this talk. So you can apply it to our graph. You see that gamma 1 is 0.309, and then if you apply it, you get 0.449 for gamma 2, which is actually quite close. Like the right bound is 0.447. Okay, so you apply this, you get 0.449. But anyway, so you can generalize this, and it says that, okay, if you have a d-dimensional complex and all base case graphs are 1 minus alpha by d expander. So again, remember, these base case graphs are those coming from faces of codimension 2 or dimension d minus 2. Then your whole complex is a local expander, and it looks like this, like 1 minus alpha by d goes all the way to 1 minus alpha by alpha d. Okay. So let me just say a few remarks about this. So this theorem has found a lot of applications in this field because, in many cases, to prove that the complex is a local expander, you just look at the eigenvalues of these top faces, and they're usually easy to bound. And there's a lot of applications. Like here's one I did with my co-authors a few years ago. We applied this to so-called the independence complex coming out of a matroid. And there you can actually show that all base case graphs are 0 expander, and that would imply that your complex is a 0, 0, 0, 0 local expander. Now, what is the downside? There are two downsides. One is that you need all base case graphs to be good expanders. Even if a single one of them is bad, you're doomed. You cannot use the theorem. The second downside is that the eigenvalues go up. So the bounds go up. Even if you have like 1 minus alpha by d for the gamma 1, as you go to gamma d, they keep going up. And the reason I'm saying this doesn't make sense is that if you simulate like some simplicial complexes, you see that eigenvalues go down as you go to phases of lower dimension. So some experts actually conjecture that maybe for some special cases like sparse complexes, you have to have this increase. But anyway, so okay, now let me tell you what we prove. Okay, I want to tell you an informal version, and then I'll make some definition, and then tell you what we actually prove. Roughly speaking, what we prove is that if the if the base case graphs on average are 1 minus alpha by d expanders, then you have a local expander. Then you have something like a constant, constant by 2, constant by 3, all the way to constant by d local spectral expander. Okay, to say what we actually prove, I need some definitions. Okay, first I need to define to you what a partite complex is. Our theorem is only for partite complexes. So what is a partite complex? Let's say you have a d-dimensional simplicial complex. We say that this is a d plus 1 partite complex if the one skeleton of the entire complex is a d plus 1 partite graph. Okay? What that means is that every facet must have exactly one vertex per part. There must be d plus 1 parts, and every facet has exactly one vertex per part. So if you look at these base case graphs, which come from faces of codimension 2, they must have d minus 1 vertices. So they have one vertex from each part, except missing 2. They miss like some parts I and j. So maybe they miss 1 and 2 in this picture. So you can really think about this base case graphs as like a bipartite graph, because they have one vertex from every part and only miss 2 parts, and then you get some edges between those missing parts. So there will be a bipartite or 2-partite graph. Now, let's fix a part I. I say that degree of this part I is the number of parts j for which there exists a bad base case graph, a bad phase tau on parts I and j, which is not a zero expander, okay, which has a positive expansion. What is special about 0? Nothing really. I mean, our theorem doesn't care about 0 so much. It's just that in the application, 0 really shows up. So that's why I'm differentiating that out. So again, I'm going to show you an example in the next slide to make this sense. But anyway, again, so you look at I, you look at the number of parts j, that there is a bad phase between I and j, positive expansion. And then delta will be the max degree of all of the parts. Okay? So let me show you an example. Hopefully this makes more sense. So what is the example of a partite complex? One example is a coloring complex. So what is a coloring complex? Let's fix the graph G with d plus 1 vertices. And let's say that we want to look at proper coloring of this graph. So I have qi colors available to color vertex I. So you can look at x0. X0 corresponds to coloring vertices with their available color. Like here, I'm looking at the graph with 3 vertices, 1, 2, and 3. 1 is connected to 2, 2 is connected to 3. You can color 1 with blue or red. You can color 2 with red, blue, or yellow, and so on. So my x0 will just be the set of colors available to color your vertices. And then x1 will be proper coloring of edges. But in general, xi would be partial proper coloring of the vertices of your graph. And xd will actually be the set of all proper coloring of all vertices of your graph. So you can see that this is a partite complex because it has one vertex from each part. Your maximal facets will have one vertex from each part, corresponding to choosing a color for each vertex. Okay? And yeah. Okay, so let me actually also tell you about the links of this complex. If you fix a tau, let's say I fix coloring vertex 1 with red, then that means that because 1 is connected to 2, it means that I cannot color 2 with red. But I can color 3 with red because 3 is not connected to 1 in my graph. So the link would look like this. I would delete red from 2. You would have a bipartite graph on parts 2 and 3. And then each pair of colors which are not the same will give you an edge. Because I cannot color 2 with blue and 3 with blue because 2 is connected to 3. But every other pairs are feasible. Here's another link. If I color 2 with red, then I cannot color 1 and 3 with red anymore because 2 is connected to 1 and 3. So the remaining complex would be this. And I can color both 1 and 3 with blue because there is no edge from 1 to 3. Okay? Is there any question? Does this definition, partite complex, make sense? So, okay. So now let's look at eigenvalues of the base case graph of the coloring complex. So base case graph now again means that you color all vertices of your graph except two. You're missing two vertices. So let's say I miss vertices I and j. I've colored the rest of the vertices. And then there are two options. Either vertices I and j, which are uncolored, are not adjacent in the graph, then they don't really care about each other. Any color that I choose for I can also choose for j. There is no constraint on them. So you get a complete bipartite graph, which is a zero expander. The second case is that the two remaining vertices are actually connected in the graph. Then they cannot be colored with the same color. So the graph that you get will be a bipartite graph where a matching is removed because I cannot color I and j with the same color. Like I remove the red edge, green edge, yellow edge, and so on. And sort of you can prove that it's like qi minus degree of I expander. In fact, minimum of qi minus degree of I and qj minus degree of j. That would be the expansion of this graph. But okay, that being said, the delta I, so now going back to delta I was the number of j's for which there is a bad base case graph between I and j. If I fix some vertex I, the number of j's for which there is a base case graph with positive expansion are exactly the set of neighbors of I in my original graph. So delta I would be equal to degree of I, and delta will be the degree of the max degree of my graph. Okay, any question? Okay, so now having that, I can tell you a simplified version of our theorem. So we say that, let's say you have, again, d-dimensional complex, or d-dimensional d+1 partite complex, and suppose all base case graphs which have positive expansion are 1 minus alpha by delta expander. Okay, so delta is like max degree of the parts. And the thing is, in principle, this delta could be much smaller than the dimension d of the complex. So then I will get a local expander, and eigenvalues go down. Okay, so I don't need 1 minus alpha by the dimension of the complex. I just need 1 minus alpha by the degree of the max degree of the parts. And okay, so you can see that, in fact, 1 minus this. If you look at sort of the average expansion of the base case graphs, it will be 1 minus alpha by d, because 1 minus alpha by d is just delta by d times 1 minus alpha by delta. One other thing is that if max degree of the parts is equal to the dimension of the complex, you get back the original trickle-down theorem. But if this delta is a constant, you actually get something much better. You get that eigenvalues go down. And this is the setting that the trickle-down doesn't work. Okay? So I want to tell you two applications of this theorem. But is there any question at the moment? Yeah.
Should we go back to the previous slide for a second? Why is it obvious that if I and j are not adjacent, you get the full bipartite?
Because no matter what you color the rest of the vertices, any color you choose for I, you can choose any other color, or even that color for j. There is no constraint between I and j. A coloring for I doesn't enforce any restriction on the coloring of j.
Like it can't be propagated through the remaining?
There is no remaining thing because you have fixed the coloring of the rest of the vertices. So the remaining, the only uncolored vertices are I and j. There could be some colorings of I and j which are absent because of the rest of the vertices being colored, but modulo that. Maybe you can look at this example also that we had here, right? Once we colored vertex 2 with red, because 1 and 3 are not connected, you would have a complete bipartite graph. In this case, it's just one edge, even though this is the same color. So you get zero expansion here. But in the other case, when you color vertex 1 with red, you would have this graph, and it's not, because 2 and 3 are connected. For example, you cannot color 2 and 3 with blue. So it's not a complete bipartite graph anymore. And its eigenvalues are positive now. Okay. So good. So now I want to tell you about the application. So the first application is for the coloring complex. So suppose that you have a graph, you want to color it with 2 plus epsilon delta colors. So here I'm using notation. I'm also using delta for the max degree of the graph, but it's okay because delta was the max degree of a complex, and we said that the degree of the complex and the degree of the graph are the same here. But anyway, so you can say that if the number of colors is more than twice the max degree, you have a local expander, and the proof is just what we talked about. You can just plug in the previous slide, say that if you have more than 2 delta many colors, all base case graphs are essentially 1 over delta expanders, 1 over 1 plus epsilon delta expanders, and then apply the trickle-down theorem to say that you have a local expander. So the consequence of this is that you can prove that the global dynamics on the set of proper coloring of the graph mixes rapidly. Okay? This is something we already knew using other techniques like coupling, but it now proves it using this machinery. Okay? Now, the second application is more interesting. So it's for sparse complexes that already have a lot of applications. So let me a little bit tell you about them. So what is a sparse complex, or a so-called Ramanujan complexes? So these are like a sequence of high-dimensional expanders that the number of their vertices go to infinity as you go along the sequence, but the number of faces that contain the number of facets that contain any single vertex remains constant. So you have a sequence of d-dimensional complexes. There's the size of x0 go to infinity, but the number of facets that contain a single vertex remain a constant. The first construction of them is by this nice work of Lobotsky, Samuels, and Vishney, where they basically look at the folding of the Brouat-Titz complexes, and they added it to a perfect expander graph. And they show that these foldings don't change the expansion or the sparsity. And then they bound the eigenvalues of the Brouat-Titz complex. So I want to tell you how you can use this new trickle-down theorem to prove a better bound on the expansion of this Brouat-Titz complex. So what is this Brouat-Titz complex? Here it is. You fix a prime P. You look at your vertices will be all proper subspaces of Fp to the D, or to the D plus 1. Xi, faces of dimension I, will be any chain of consistent subspaces, W1, W2, up to Wi plus 1. Okay? So for example, here I have faces of, faces of dimension 2. They correspond to choosing, maybe I have like P equal to 2 and D equal to, I think, 2 as well. But yeah, this correspond to choosing a subspace of dimension 1 together with a subspace of dimension 2, that the subspace of dimension 1 is a subset of it. Okay? So these are like also called some maybe chain complex. They correspond to chain of subspaces. One is a subset of the next. And you can see that these are partite complexes where part I correspond to subspaces that have dimension I. So you can see that your facets actually would have one subspace of dimension 1, one subspace of dimension 2, all the way to one subspace of dimension D, and that's why it is a partite complex. Now let's look at eigenvalues of the base case graphs. So again, you want to look at which parts are missing. So let's say parts I and I plus 1 are missing. So it's something like this. So you have subspaces of dimension 1, 2, all the way to I minus 1, and I plus 2 all the way to D, but you don't have an I and I plus 1. And in this case, actually, it's not that hard to see that the second eigenvalue of the graph you get for subspaces between I and I plus 1, which are consistent with the rest of the chain, is 1 over root P. P is the prime of the field. But a second case is when you have I and J where they are not adjacent. J is more than I plus 1. So you have all subspaces of dimension 1 up to I minus 1, and then you don't have I, and you have some other stuff in the middle. You don't have J, and then so on. And then in this case, this is a good case, because I and J don't really enforce any constraint on each other. Like if you choose any subspace on I, you can choose any other subspace on J. So in this case, actually, you get a complete bipartite graph. Second eigenvalue will be 0. So the nice thing is that now if you fix I, the only bad parts with respect to I are I plus 1 and I minus 1. Any other part will give you 0 expansion. So your delta I will be equal to 2, and delta will be equal to 2. So actually you get that this complex is 1 over root P all the way to 1 over D times root P local expander, as long as P is more than some constant. So to summarize, basically you can apply the same technique to this other construction of sparse complexes by Kaufman, Oppenheim, and O'Donnell-Pratt. Basically, you can, like in a black box way, you can improve the local expansion of what they could prove. Like the previous bounds, they could get that the complex is 1 over root p local expander when p is more than the dimension squared. But now you can say you can get a local expander even for a constant p independent of the dimension. Okay, I still don't know applications for this, but okay, I'm hoping that some will come because these Ramanujan complexes have found a lot of applications. Okay, so I'm running out of time. I just wanted to tell you one more. Let me tell you two more things. So I haven't still said the full description of the theorem, which is that what we really prove is that we define this epsilon ij to be the worst expansion of all base case graphs that miss parts I and j. And then we say what we say is that if for every I the average of epsilon ij is less than 1 minus alpha by d, then you get that one skeleton of the complex is like 1 minus alpha by alpha d expander. Okay, so this average really is some weighted average, but okay, so there is some little mess going on, which maybe let's not get through it at the moment. So I just wanted to say one more thing before I go. So I started working on this in this area maybe a few years ago, where we sort of use these high-dimensional expanders to study Markov chains and basically random walks on bases of bases of matroids, and there is connections to geometry of polynomials and so on. And since then, there has several tools from this field have been used to study random walks and polynomials. But in this work, we kind of did the opposite. So we started with a result, like we knew that the random walk on proper colorings of the graph, of any graph mixes in polynomial time. Then we looked at the corresponding complex. We knew that it must be a high-dimensional expander, but we noticed that this trickle-down theorem cannot give you anything, cannot give you any proof. So we said that, okay, maybe there is a better trickle-down theorem, and okay, we could prove it. So the reason I'm saying this is that I expect to see a lot more interaction of these fields in future. And maybe now is the time to go back and see a lot of theorems that Markov chain community have proven, and they can be turned into some theorems about high-dimensional expanders. All right, so let me stop at some open problems. Maybe, okay. One of them is to get rid of the partite complexes, get something for all complexes. Or another one is to maybe try to find some applications of this new bound, spectral expansion bound we prove for Ramanujan complexes, and yeah, so on. Okay, let me stop here. Yeah, I haven't tried to optimize the constant, but this root p is something you should expect. It's sort of the same analog of the Ramanujan case, but I don't know really what the best constant is, and we don't even have the analog of Alombapana. I don't know if any lower bounds can be shown, but yeah, it's all off the graph. Any other? Yeah.
Other case, so what's the difference? Is it a different chain? Like the point here?
No. So no. So there are other ways of applying it. So I guess so So one way to apply it is that there are these proofs for analyzing the coloring random walk where you use coupling. Those can be turned into the fact that the corresponding complex is an expander, like as a black box way. Another thing we did was to have a more sophisticated proof to, similar flavor of, trickle-down theorem, get a better bound for edge coloring. So like using this, it's hard to go below 2, like for vertex coloring, but for edge coloring, we can go to something like 1.6 delta colors as opposed to 2 delta colors. But yeah, it's a very active. There are a lot of people trying to nail down this coloring complex. It's hopefully in a few years we'll know the answer. All right.